Welcome back, ladies and gentlemen. In this video, we're going to be looking at static electricity and electric charge, along with possibly getting into electric force. So here we go. I want to start with a quick look at atomic structure. Now this is kind of an old school way of looking at an atom. We've got a nucleus where we have positive charged protons and neutral neutrons. And around the nucleus, we have the negatively charged electrons. Looking at this, we can see that we have 6 protons making this bad boy carbon. And so, 6 of those guys. And we see 6 electrons. And the neutrons are neutral, so they have no charge. Protons have an inherent property to them. They do have a mass. But another inherent property, inherent just means it's kind of like built into that that particle, is the amount of charge. And the amount of charge you typically think of as just +1. Same thing with an electron, except you think of it as -1. So what you've got here is a total of 6 negative charges. So 6 times negatives, and here 6 positive charges, 6 times the positives. And looking at the total, neutrons are neutral, they have no charge to them. Looking at the total, it sure looks like things cancel out. So overall, neutral or balanced charges are balanced out. So for every positive, there's a negative. Okay, fair enough. Now, what if we take one of these electrons and somehow strip it away and get rid of it? Well, then clearly things are no longer balanced. We would have 5, and then we would have unbalanced, or we would have an overall positive charge to this carbon atom. There would be 6 positives, but only 5 negatives. There's 1 positive left over. So you would have a positive ion. An ion is simply a charged particle. It has an overall charge to it. I should say a charged atom. Okay, so an electron can't be an ion, a proton cannot be an ion, but an atom that has a positive or negative charge is an ion, right? I think most of you have had chemistry, so this works out. But there you go. It's a charged atom, electrically charged atom. These are electric charges. But what if it's just the other way around? What if we have not only an electron there, what if we add on another electron somewhere? And that is possible. So in that case, we'd be back up to 6 negatives plus another 1, we'd be back up to 7 negatives, and still just the 6 positives in the nucleus. So it'd be, in that case, overall, you'd have 1 leftover negative charge that is not balanced. You'd have a negative ion. Okay. So atoms can be neutral, they can be positive ions, or they can be negative ions, depending on what's going on with the charges. But remember, we're not changing the protons. If you remember a little bit about your chemistry, if you change the number of protons, you change the element. That is a nuclear reaction. That's not a chemical reaction. A chemical reaction deals with the electrons around the outside. And we're not going nuclear on this stuff, so don't sweat it. But you can create an ion by adding or subtracting electrons around the outside. Easy enough. By the way, it does not have to be carbon. It could be just about any element you want to talk about. Well, the thing about this is, some of these electrons are, in some elements, they have a greater tendency to break free and move around. And that makes some materials good conductors, while other materials would be good insulators. So we've got right away conductors versus insulators. And a conductor would allow the charges to move around. In fact, a conductor, it holds on pretty loosely to these outer electrons, and so they're more easily pushed around. An insulator holds on pretty tightly to all those electrons. And it's not just necessarily individual atoms that hold on to the electrons, it might be the chemical bonds themselves. We do have to look into that. This freedom of the electron's freedom to flow around is largely controlled by those chemical bonds between the atoms. To understand this, we need to look at this guy right here for just a moment. The periodic table of the elements. Now, we're going to separate this into two very, very broad general groups. And it kind of goes like this. A little stair-step action right through here. And we're going to go between 117 and 118 right there. And so here's the deal. This separation puts on the left all of the metals or metallic elements, right? And what's interesting, if you really pay attention, hydrogen is over here typically in the periodic table, and sometimes hydrogen behaves like a metal. Quite often it does not, so you might sometimes think of hydrogen as better belonging on this side. It kind of depends on conditions. Don't worry about hydrogen right now. This is a very general, very broad thing we can say. On the other side, generally this way, are nonmetals. Okay, things like your oxygen and your carbon, your nitrogen, a few others, right? There are some in this vicinity, of this division line. Some of these sort of don't fall into just one or the other. They kind of share some properties from either side of that line. Those are sometimes called metalloids, sometimes called your semiconductors. And so that's why silicon is a semiconductor. You've heard of this place called Silicon Valley, where they make a lot of semiconductors. Well, silicon is a semiconductor. It sort of has properties of metals and sort of has properties of non-metals. Well, you know about metals, they are good conductors. And so there's some more detail we need to go into here. But just very generally, no, you do not have to memorize this, but I want to show you that large majority of the elements have metallic properties, and they are good conductors of electricity and electric charge, whereas a smaller number, typically, under typical conditions, do not conduct electricity. They're better insulators. Okay, so now, conductors and insulators, right? And so what's the big deal here? Well, it comes down to chemical bonds. And we're going to come back to that periodic table in just a moment. And the reason why is this. If you were to bond a metal and a nonmetal, then what you would get is an ionic bond. Now, what you may be saying to yourself is, oh, it's an ionic bond, so it's an ion, so the charges are whack, and I get easily flowing charges. It's going to be a good conductor. Unfortunately, no. Ionic bonds, substances like that, for example, you could take, let's say, a metal like sodium and a nonmetal like chlorine, and you put them together and you get sodium chloride. You get table salt, but that is one of the classic examples of an ionic bond. Table salt. And the thing about ionic bonded substances, they actually don't conduct electricity. They're very poor conductors. Well, what if you took two nonmetals? Nonmetal plus nonmetal. Nonmetal. I can spell, I swear. What you get here when you have a metal and a nonmetal come together is you typically get a covalent bond. Now, don't sweat yourself if you're not into the chemistry that much. I'm not here to teach you chemistry. But if you look at this, well, a couple nonmetals, covalent bond. You might have carbon and oxygen, two nonmetals, and they could bond to form, say, CO2 gas, or carbon monoxide if you prefer. That might be a two right there to help balance things out. Or even pure carbon. Pure carbon in a three-dimensional crystalline structure like diamond is an extremely poor conductor. All those carbon atoms bonded to each other in that way. So poor conductors all around with these two types of bonds. And so this is crazy. Now, if you did something weird and say took a bunch of salt and heated it up until you melted it, well, the liquid salt would conduct electricity. Another thing, if you dissolve salt in water, the water itself would be a good conductor at that point, but it's not the salt anymore. You're talking about water. These are poor conductors in general. They do not conduct electricity. They don't like to. Well, then, what the heck, Mr. Woods, is going on? Where do we get our good conductors from? They come from when you combine metals together. Metal plus metal. You get what's referred to as a metallic bond. And with metallic bonds, let's say you're taking iron, right? Well, iron is located right here in the periodic table. And so you're going to take some iron, you're going to bond it to other iron, and you might bond it to more iron, and you keep going, and you get a lot of iron. But there's no specific chemical formula here for this necessarily, not for our purposes anyway, because what this ends up looking like is something like this, where you might have all those iron iron atoms. They're bonded together in this chunk of iron that you've got. But in between all the atoms, which consist of a nucleus plus some of the electrons, the outer free electrons, these so-called free electrons, they are held on so loosely by those atoms, they float around in between all the atoms very easily, very freely, almost like solid chunks of material in a soup of these electrons, with the electrons flowing all around in random ways, not doing a whole lot until you put it to work for you. So this is how metallic bonds might look if you were able to look at them and actually see the atoms and loose or free electrons. Now they're titled positive ions here. Well, if you take an atom and let go of an electron, it becomes a positive ion. It's just that simple. All right. So there are the three general types of bonds, and it is this guy that will allow you to conduct electricity. Covalent bonds and ionic bonds do not. How about that? Well, now, why? Why are these metals such good conductors? The atoms hold onto their electrons rather loosely. I think I mentioned that. So the electrons are bumped out of place easily. So if I were to force an electron, negatively charged particle, in right there, it's going to push this guy out of the way, maybe this way, and it's going to bump that guy that way, and he's going to bump, and they're going to just do this until something comes out the other side. And you know what this might be? This might be metal in a wire. And you're forcing charged particles through into this side of the wire, and all the way out the other side, you get charged particles at the other side. On a wire, a very long, thin wire, it may not be, let's say you got a wire here, it may not be this charged particle right there that you force into this end that you get out of this end. Not necessarily. But the cool thing is, all of these charges are identical. If they're negative, they're identical to each other. It's really simple and slick that way. Well, all right. So electrons get bumped out of place very easily, and they're easily made to move. And moving charges are an electric current. Now, we're not looking at current electricity and moving charges necessarily right now. That comes later. Next thing. You know what these are? These guys are cool. Right. I can turn it over. Oh, yeah. So we're talking about magnets right there. Well, okay, we're not looking at magnets necessarily here. But magnets behave in a way similar to charges in a couple regards. So you've heard that opposites attract and likes repel, right? It's true for magnets. So if I get these oriented a certain way, they attract each other. And if I take this blue one, take the blue one and just flip it over, and now it's going to repel the red one. Doesn't like it. So it's very same thing with electric charges. There are two kinds of charge. So two kinds of charge. There's a positive kind of charge and a negative kind of charge. And if you get a couple positives nearby each other, they want to repel. If you get a couple negatives nearby each other, they want to repel. But you get a positive and negative near each other, and they will attract. Opposites attract. Now, here's the crazy thing. These charges already exist in everything. Literally, if it's made up of atoms, it has these charges in it. I mean, think about this. It has all these protons. It has all these electrons. The charges are already there. And that's cool. But they're usually balanced. It's only when charges become unbalanced or separated from each other that things get interesting. Now, little interesting trivial number for you. You do not have to memorize this. Not on the test. But in the human body, there may be as many as 4.6 times 10 to the 28 charged particles in your body right now. That's huge. That's a 4 and a 6 followed by another 27 zeros. That's an insanely large number of charged particles. So, we'll look at the amount of charge later on that really represents, but the charged particles are all those protons and electrons in the atoms that make up your body, right? Now, charges do exert forces on each other, and that force acts across a distance. So this is kind of trivial here. Back to important points. There is a force caused by electric charges. Oh, by the way, this is not Fe for iron. This is force of electric charges. That's just the notation that I'd like to use. And this force due to charges, that's what that is. Well, it can act across a distance. It does not need a cross. I can spell. It does not need to be in physical contact with something else. Okay. They do exert forces on each other. That's real important to understand. There is this thing called the electric force, and it acts across a distance. You know what else can act across a distance? You were thinking it. Right. This is much like gravity. You don't have to be in contact with the Earth for its gravitational pull to be affecting you. Another important and interesting point here. The force caused by electric charges is stronger when the charges are closer. Closer together, I'll write that. And so, well, you know what? You know what else does this? The closer you are to a planet, the stronger that planet's gravitational pull will affect you. You go farther away from Earth, its gravitational pull on you gets weaker. Oh, wow. So, now what's weird here, though, what's going to be different in at least one way, is that this force that we're talking about, not gravity, but the force due to electric charge, it can attract, and that's like gravity does, right? But it will attract when you have positives and negatives nearby. But it can also repel. And this is maybe when you have a couple negatives near each other or a couple positives near each other. right? So this first part, it can attract. That's like gravity. Gravity attracts. The second part, electric charges can also repel each other. Gravity cannot do that. Gravity will only attract. Okay, now, there was a guy, and his name was Charles. Charles Coulomb was his name. And he's a big deal. Make sure I'm spelling his last name correctly. I think it's C-O-U-L-O-M-B. And he was a big deal because he did a lot of work with electric charge and figured out a whole bunch of stuff regarding this electric charge. In fact, way back in the 1700s. So check this out. Around 1785, I believe it was. He studied this relationship between electric charges and the distance between them and the force of attraction or repulsion that they create. And what he figured out was that electric force is proportional to the amount of charge that exists in one particle and in the other multiplied together. So if you have, and that's a lowercase q, so q represents amount of charge. You know how kind of like m represents amount of mass? Like that. Q is amount of charge. Okay? So this is the amount of charge in one particle multiplied with the amount of charge in another particle. Well, the force due to those charges, the electric force, is proportional to the amount of those two charges. If you have more charge, you'll have more force. Coulomb also figured out the relationship with distance. He said, well, the electric force is proportional to the inverse of the distance between them, where r is the distance between the charges. Distance between the charges. And so combining these two things, right? There's one more proportionality we can talk about. We haven't written an equal sign yet. That's coming. We can look at this. We can say charge A and charge B, and then we divide by r squared. Okay, so it's not yet an equation, and there's a reason for that. But Coulomb was working all this out. He was working this out even before electric charge was really understood very well. A lot of the understanding of this stuff came a little bit later, but he was looking at the effects of these charges. That little beeping was something, don't worry about it. And so now we got to look at that, right? I want to show you, to make an equation from this, get this going down here. We're going to wrap up this video, and we'll do more in a part 2 on electric charge. So there's going to be an equation. Now, to make an equation and be able to write an equal sign there, there's going to have to be something else that goes in this equation. And at this moment, we'll just call it a constant, some constant k. And so we can write charge A, we can write charge B, and we can write r squared as the distance between them, right? But this constant, Coulomb did a whole bunch of work to figure out what this constant looks like. And so we know its value nowadays pretty precisely, where k is equal to, check this out, this is a number you're going to want to know, 9 times 10 to the 9th power, and it does have certain units with it. It would be Newton meter squared per, oh, there's a new unit right there, capital C. That's not a lowercase c, it's a capital C. Coulombs squared. So Coulomb is the unit of electric charge. Let me write that down up here for you. Check that out. You know, with mass, we measure mass with kilograms. Well, with charge, we measure charge with coulombs, or capital C, right? So you want to learn that. You want to be able to talk about coulombs if you're talking about how much charge there is. And the symbol is a capital C. Now that's the symbol, or the shorthand way of writing coulombs. If you want the variable for charge, you use a lowercase q in most cases, most of the time. Maybe, depending on what class you go to in the textbook you're using, might be a capital Q. But we're using lowercase q here for charge. Okay, so I want to leave and end this video with this. Check this out. You've got an equation for the amount of force caused by electric charges. That looks a lot like